And a lot of the applications of survey data are people simply reporting summary statistics. Think people saying things like only 5% of people walk more than 15 minutes a day. Only a few percent of people do the required amount of sports and exercise. And this is just this is an attempt to maybe get a bit more out of that data than just reporting these straightforward statistics. Okay. So as I said, we have these 17 variables. We have our 4 energy intake variables, our 3 energy expenditure variables, and all the other socio-demographic variables. And we create a Bayesian network out of this data. So as I said, each variable is represented by a node. And what we can do is generate any Bayesian network and draw random arcs between each node. So we just have some network. And then what we can do, we can score that network based on the likelihood of the data given that network. Then what we do, we iterate through a series of these networks. So we'll mutate a network, we'll change it in some way, we'll add an arc, we'll switch an arc, we'll change the parent of arcs to generate a new network. And then we can also score that network. And what we have is a sampler, so that we end up with a selection of the best network topologies. Right, so if you look here, this is another simple Bayesian network. I'm representing perhaps whether a certain patch of grass is wet or not. You can see at the bottom we have wet grass, and we can tell that the state of wet grass is influenced by both whether it's raining or not and whether there's sprinklers on. Both of these factors are influenced by whether the weather is cloudy. So what we have on the right-hand side is a data set that represents some observed data. So what we can do is use this network on the left to estimate the probability of observing this data on the right. And that will come out with a probability, or a likelihood, and that will be small typically, because we're looking at the probability of the data given the network. Now if we change this network in some way, so that what we have now is a different model, the relationships between the variables are different. And what we can do is score the same network based on the data. Now what I would like to see from this is that this network ends up with a far lower score than this network. Because this network, you can intuitively see that it would make sense it would just make sense on an intuitive level. We can see that wet grass is indeed influenced by rainy and whether the sprinkler's on, whereas this network is fairly nonsensical, so we'd hope that the data would reveal this about the true network. Right, so there are a vast number of possible networks. When you have 17 nodes, the number of possible permutations and combinations is mind-boggling. There is no way we can iterate through every single combination of arcs and vertices. So what we have to do is find the best networks. And to do this, we use the sampling technique of finding a network, changing it in some way, moving to a new network, scoring that new network, then moving to another network, scoring that network. And what it is, the sampler is set up in such a way that the probability of moving from one network to another network is weighted by the likelihood of that network. So we tend to migrate towards the best networks. And in the final sample at the end, the best networks are represented according to their probability, or likelihood, their likelihood. Right, so what we have now is a series or a sample of possible networks, which isn't that helpful to us at the moment. So within a Bayesian network, within a structure like this, we have arcs and vertices. And what we can begin to do if we have lots and lots of these is that we can begin to pick out structural features that they share. For example, if we have a big sample of 100 of these networks, and there's always an arc between raining and wet grass, that means that we can be fairly sure that in reality there is a real relationship between these two nodes. So we're looking at structural features. Now this is the results from our data. I apologize if you can't see it very clearly. It looks slightly blocky. But a black arc means that in our sample of network structures, that there was an arc between the two nodes in every single observed topology. So from that we can be confident that there is a real relationship between the two. So this is a graph for males. So if you look between age and recreational physical activity here, or hours of sport, there's always a relationship. There's always a relationship between age-independent children, and a lot of the socio-demographic factors are very, very highly correlated. So you always observe arcs between them in every single sample topology. The red lines are arcs that are observed less of the time, between 1% and 90% of the time. So these are still probable relationships, but they're not as certain as the black arcs. And the yellow ones are ones that are less frequently observed. So they might still represent real relationships, but we can be much less certain of them. Okay, so this is the data for the male. Some interesting things that we may want to look at is social class, NSSEC, the National Statistics Socio-Economic Classification, is always related to, there's a link between fruit and vegetable consumption, there's a link between occupational physical activity. So we begin to know that these socio-demographic variables are important in people's obesity-related behaviors. Now, if we look at females, the graph in females, we see a similar kind of structure with the important socio-demographic factors all correlated together. And one interesting thing you may notice about this graph is that age isn't associated, doesn't have a black arc with recreational physical activity. However, education does. Which means that in women, we can say that women, education and social class is an important determinant, or it's highly associated with recreational physical activity. Whereas in men, age is a much more important determinant. If we look at social class, it's always correlated with fruit and vegetable intake and other dietary factors, which may be of interest. And we also observe an effect of ethnicity on certain energy intake indicators, which may represent something that policymakers can look at. So what the purpose of this work is we can identify these relationships that standard cross-sectional observations wouldn't really give us that kind of, it wouldn't really explain that data. Because what tends to happen is that because the data is so correlated, it looks like the effect is at any cross-section you make. So if you just took a simple cross-section of women's physical activity levels and their age, you may observe a significant effect, which would be easy to attribute to differential behavior and age. But using this kind of technique, we can maybe say, well, that may be true, but we can look at other factors that are highly correlated with age that may actually be more, that may be more likely to have a causal relationship with recreational physical activity, like dependent children and social class and occupation, and that kind of thing. So we can sort of almost drill down better into the data. What we have here is essentially a big sample of models, which we can then use later on to possibly even make predictions about future data. And we have a big swathe of models that we can almost average together and use to predict certain things about distributions. And the other thing it allows us to do nicely is to generate what I call useful statistics, where we may want to say, for example, what is the probability that a group of males, that maybe middle-aged males who are unemployed, fall into a certain recreational physical activity group. And because the data, because the health survey of Finland is only based on 11,000 people, when you start to break that down and say, right, if I want to take the males who are within a certain age group, who are unemployed, you actually start getting very, very small numbers. So your estimate becomes becomes almost worthless. Whereas if you have a more of a global model and you're conditioning across probabilities, you can perhaps make slightly more informed guesses. And there we go. Questions? Yeah, essentially. Yeah, because as I said, this data is highly correlated. If you use something maybe like a logistic regression model, you choose a dependent variable and you choose your independent variables. You can't model all the variables together. So we're looking at, no, exactly. Yeah, when you make a logistic, yeah, when you do a standard analysis, you assume that all your predictors are independent, which isn't generally the case. Yeah, we're not modeling the outcomes on specific variables. We're just looking at what we're essentially doing is trying to explain the associations between the variables as best we can, and then making inferences from that. The structural features, no, I've got it set up so that you can pick out a certain structural feature. In this case, we use the number of times an arc occurs between two nodes as our feature. And it's a fairly simple sort of computational process. I've got scripts written that will just count them and then average them. So we end up with a number between 0, which means you never observe the arc, and 1, where you always observe the arc. Because we have... No, that's fine. We have a... So as I said, if we look at this, if we go back to something like this diagram, this is a single Bayesian network. And in this single Bayesian network, there's an arc from wet grass to cloudy. Whereas if we go to this other graph, there is no arc between wet grass and cloudy. So if we have a situation where this network appears 99 times in our final sample, and this network appears once, we would give that wet grass to cloudy arc a score of 0.01, which would tell us that it's not very important in explaining the data. Whereas if we observe an arc between raining and cloudy in every single network we sample, that tells us that that is an important arc in explaining the data. No, well, to an extent we do, but you send that through an iterative process. So we'll start off with a network and then change to another network. How do you make that change? You do it computationally. So there are maybe certain moves, so you might want to, so maybe there are basically 3 moves which you implement, which are add an extra arc, where you, from a network, you add an arc to a random pair of nodes, you remove an existing arc, or you change the direction of an existing arc. And that's how it gets, and that's how you start to move from maybe networks that badly explain the data to networks that explain the data quite well. Okay?
So does that help you determine the direction of relationships?
No, well, yeah, that's another thing. It's very, very easy and somewhat tempting to start assigning causality to these networks, whereas we have to be very, very careful not to say this is causal or not causal. No, we're just purely trying to explain the data. Causal inference is something that is very tempting to get involved in when you're looking at this kind of network, but it gives us no information on the direction of the effects. What I use, the programming is done in C#. And then I use both Stata and R to sort of process the outputs of that system. A run, say what we do 1 million iterations. So we move from our start network, we perform a move to another network about 1 million times. And we sample every 100 networks. So that gives us a final sample of 10,000 networks, of which we discard the first 5,000 because you need to wait for your sampler to move into the space of good networks rather than your random starting space. And that takes about 11 hours for an iteration of 1 million, to run 1 million moves. Yeah, it probably doesn't take 5,000, but it depends on certain things like the size of the data set. If you've got a very large data set, your distribution, your likelihood distribution of all possible networks is much more peaked, which means that the good networks are much, much better and the bad networks are much, much worse, which actually makes it more difficult to go from the good to the bad and the bad to the good. So it does depend on certain other things. But 500,000 is probably a safe, it's probably a safe a safe point.